Okay, our last video ended abruptly. We have a 15-minute time limit on the length of these videos, and I wasn't watching the clock, so it ended abruptly. So where we left off, we had a table with 200 bytes of data in our table. So the next step was I was going to position the table near the end of the flash memory area. So in the include file, there is a name called flash end, and it contains the address of the end flash memory, the last address in the flash memory. So if I do a .org, I can position my table at near the end of that memory. So I'm going to say flash end, and my table is 200 bytes, which is 100 words. And what we're going to do is subtract 100 because this is word address to memory. And then what I want to do, just to demonstrate, is I'm going to position the table so it starts on an even multiple of 16. And in order to do that, what I can do is I can truncate or mask out the last 4 bits of the 16-bit number. So I can mask it out by using a number that has 12 ones in a row and then followed by 4 zeros. And when you do a bitwise AND, every bit that's ANDed with those zeros becomes 0, so it rounds a number off to the nearest 16. So I'm going to AND it with a hexadecimal value of FFF0. And that should put the table near the end of the flash memory. In fact, what we'll do is we'll assemble the file, start the debug even though we're not ready, but we can look at the memory and see where the table is in memory. So I'm going to assemble this, and so it shows on here data. We have 200 bytes of data in our memory, and our code size right now is only 16. So I'm going to start the debug so that we can open the memory view. So the debug started, and view memory. And then I'm going to go to the end of the memory, and you can see here the data starts at address 3F90, and it goes all the way down here to approximately 3F 1, 2, 3, 4, 5, 6, 7, 8, 3FF8, or, oh wait, 3FF4. These are word address. Yeah, okay. So notice the next line starts at 3FF8. So we have 200 bytes of data stored here, and it's right here near the end of our address memory. So the address memory, you can see here when I hold my mouse over there, is 3FFF, which is 4 kilobytes of flash memory. So that's where we stored our table. Now, what we need to do is set up our X, Y, and Z pointers. So we'll set the Z pointer to point to the beginning of our table. And we have a label at the beginning of our table that's called table ADDR4_0 because it's a table I made for 4-second sweep on the servo motor. So I want the high and low byte of that label to go into ZH and ZL. So LDI, the temp, oh no, actually I can do just ZH, the high byte of the address, high, and the label name is table ADDR4_0. 4_0, okay. And then, so that went straight to ZH register. We didn't have to use a output or anything. And then LDI ZL, the low byte of table ADDR 4_0. 4_0, and I see a mistake up here. Okay, so that's the Z address. So that's going to be used for the LPM instruction. If you look at the help on the LPM instruction, you'll see that it uses a Z address, and we can use a post increment version of that so that we can do LPM temp comma Z plus, for example, and it'll load whatever the Z address register is pointing to into temp. Oh, and one other thing, I almost made a mistake here. This address is the program memory is word address. The assembler uses word addressing. The LPM instruction uses byte addressing. So the byte address is going to be twice as high or twice as many as the word addresses, because bytes are 8 bits, words are 16 bits. So what we have to do is take the word address and double it to make it a byte address. And we can double it by moving the number, shifting it left once in binary, and that is the same thing as doubling the number. So that's, or we could do it times 2, but shifting it left is effectively doubling the number. So that gives us the byte address into ZH and ZL for use by the LPM instruction. Now we want to put the table in SRAM if we're going to copy it. So we need the SRAM start address. If we want to put it there, we can. So I'm going to load X, H, and XL, that's register 27 and register 26, with the first address of SRAM. In fact, we'll even give it an offset of like 10 hex, just to demonstrate. So X, H, comma, the high byte of, now SRAM start, I think I have this right, SRAM underscore start, and I'm going to add plus 10 hex to that, just to give it a little offset. XL, same thing, only the low byte of SRAM start plus now we want to every time we use the LPM instruction, and we're going to use it with the post increment, so it will add 1 to the LPM instruction after it reads the value, uses it for an address to read the value into temp or whatever register we want to read it into. But we need to compare that Z register with a number that will tell us when we're at the end of the table, so we know when we got to the end. So we have a label here called table end, and we can load the address of that label into the Y register. So I'm going to copy that label name and load the high and low byte into YH and YL. So LDI YH, comma, the high byte of that label name. And what happened? I just copied a whole, yeah I did, okay, Control Z. Table end, right? So I'm going to 4_0, okay. And we do that for the high byte and the low byte. Okay, now we need a routine that's going to loop through and copy and move the data from the program memory into SRAM. And it's going to be a routine that has to loop over and over and over again. So we're going to need a label at the beginning of this function so that it can go through the loop. Or in fact, you know what? Let's do this. Let's make a function to do that. So I'm going to make a function, and we'll call the function. So I'm going to call it copy table with a label. Now, so we want to do a LPM instruction. So LPM, and we want to copy into temp, comma, z plus the post increment. And then we want to store the data. So we need to use the st command. I'm going to do double space and then a tab. And we want to store it at x plus, comma, temp. So that's a post increment addressing. So it's going to store it at the address x and then add 1 to x every time. So we don't have to manually add it. And then we want to compare the Z register to see if we got to the end of the table yet. So it's a 16-bit register, so we do the compare on the low byte, then a compare with carry on the high byte. So CP and Y, or let me see, Y low, comma, Z low, and then CPC, compare with carry, YH, comma, ZH. And if they're equal, we know we got to the end of the table. So, so we're going to do a BRNE, done copy, a label, something like that, right? And then if they're not equal, if we're not done copying, then we want to go back to the copy table and get the next value. So RJMP copy table, and then our label done copy, and a return from there, because we're going to use our rcall to get here. So we'll just use a return from there. So here we need to rcall to copy table. Okay, so we can build at this point and test our copy function. It's a good point to test it to make sure it all works. So I'm going to assemble this at this point, see if we have any errors, and we do have one error. Okay, undefined. So I think that SRAM start is not right. Let's try this and see if that fixes it. No. Oh, I got STRAM. Duh. I think I had it right. SRAM underscore start. Okay, let's try that again. All right, no errors now. So we can run through. I'm going to set a breakpoint here. And I'm going to, so we assembled it already. I'm going to start the simulation and look at the copy table function.